Hello, I'm Ralph Gable of the Electronics for the Inquisitive Experimenter YouTube channel. In the last video, I designed a T-configuration impedance matching network the easy way using a Smith chart. There's a link in the description and up in the corner for you if you missed that one. This can also be done with math and, well, a bit more work. And that is what I'm going to be doing in this video. I'm going to walk you through the process of designing a T-configuration matching circuit that will provide a match between the same two impedances that I used in the last video. The difference is, this time I'm going to be using the equations. Now, I will be repeating some things that I said in the other videos on designing matching networks using math because, well, I wanted this to be self-contained. If you have watched any of the other videos, then you will find some of this to be a little review on those points. But reminders are almost always a good thing for learning. I will put a link to a zip file in the description which contains the formula sheet and the octave.m file for this demonstration. If you have questions or comments, please feel free to add a comment to this video. If you find this video helpful, please click on the like and don't forget to subscribe. We begin, as always, by defining our objectives. Well, the objectives for this exercise are quite simple. The overall circuit looks like this. We have a source impedance of 10 minus J20. We have a load impedance of 20 minus J15. And we're going to operate at a frequency of 50 megahertz. Now, we have to prepare our circuit for the mathematical process. To prepare our circuit for the equations, we begin by getting the source and load impedances in the same configuration as the matching networks. If the matching network's reactance is in series, then we must have the associated source or load impedance expressed as a series combination of resistance and reactance. If the matching network's reactance is parallel, then we must have the associated source or load impedance expressed as a parallel combination of resistance and reactance. For a more complete explanation of the parallel equivalence of a series impedance, I will point you to my video on the subject. I've placed a link in the description and up in the corner for you. The transformation from series to parallel is a relatively easy one to make. But in this case, both the input side and the output side of the T configuration are series entities. So we don't have to do anything to either the source or the load impedances to move ahead. I like it. Our next step is to begin putting stuff into our equations. The equations we are going to use refer to an R1 and an R2. R1 is the real part of the impedance associated with the input side of the matching network. In this case, this is the series resistance associated with the source impedance. This means that R1 is equal to 10 ohms. R2 is the real part of the impedance associated with the output side of the matching network. Similar to the source side, this is the series resistance associated with the load impedance. Therefore, R2 is equal to 20 ohms. We will be calculating X1, X2, and X3 with our equations. What do these refer to? Well, X1 is the reactance of the series combination of the reactive portion of the source impedance and the input series component XA. X2 is simply the reactance of the single parallel component which exists in the center between XA and XC. X3 is the reactance of the series combination of the reactive portion of the load impedance and the output series component XC. Now that we know what we're going to be doing and with what, let's do the math. Well, one of the inputs to the equations we will be using is the phase. Unlike the L configuration matching networks, we get to define the phase angle. But first, we need to understand what this is all about. So let's talk briefly about this whole phase business because, well, few people spend any real time helping us understand what this means. Phase in this context has to do with the phase of the output relative to the input signal. So what do I mean by the input signal in this context? Well, in this example, we have a signal source which has an output impedance of 10 minus J20. This signal source consists of a perfect voltage source, which has an output impedance of 0 ohms and a phase of 0 degrees, followed by a series resistance of 10 ohms and a series capacitive reactance of 20 ohms. The input signal is the output of this perfect voltage source. The phase then includes the phase shift of the output impedance of our source and the effects of the reactances associated with the impedance matching network terminated with the load impedance. According to the impedance matching book that I got the equations for X1, X2, and X3 from, we can choose any phase angle from minus 180 to plus 180 degrees. Well, being the curious guy that I am, I just had to go and create an Excel spreadsheet which explores the effects of the choice of phase angle on the solution to this particular impedance matching application. Now, if you're interested in that spreadsheet, there's a link to the zip file which contains this Excel spreadsheet down in the description. What I discovered was that reasonably realistic component values existed between plus 20 and plus 170 degrees and between minus 160 and minus 130 degrees. Based on what I saw in my spreadsheet, I'm going to choose a phase angle of 45 degrees for this particular application. So beta, our phase angle, is equal to 45 degrees or 0.7854 radians. Now that we have the phase angle, we can move on to calculating X1, X2, and X3. And here is the equation for X1. X1 is equal to the square root of the quantity R1 times R2 minus R1 times the cosine of our phase angle beta divided by the sine of our phase angle beta. And we know that R1 is equal to 10, R2 is equal to 20, our phase angle beta is 45 degrees. So putting all of these values into our equation, we get this. Calculating this out gives us a reactance for X1 of a plus 10. But this is the series combination of XA, our component, and the source's series reactance. We have to disentangle these to arrive at a value for XA. To do this, we simply subtract the source's series reactance from X1. And we know that the source's series reactance is equal to minus 20, and we just calculated X1 to be plus 10. So XA is equal to a plus 10 minus a negative 20. Which gives us that XA has a reactance of plus 30. So what is the value of this component? We know this is an inductor because its reactance is positive, so I'm going to use this formula to calculate its value in nanohenries. L1 is equal to 1 times 10 to the 9th times our reactance XA divided by 2 times pi times the frequency in hertz. And we know XA is equal to a plus 30, and the operating frequency, F, is 50 megahertz. And this gives us, well, this, which yields a value for L1 of 95.493 nanohenries. When we use the Smith chart, we got a value of 95.49 nanohenries. We have an exact match. Now, on to our next component. Well, the good news is that X2 is also XB, the parallel component in the middle of the T configuration. And here is the equation for X2. X2 is equal to negative the square root of R1 times R2 divided by the sine of the phase angle beta. And we know the value of R1 is 10 and R2 is 20, and our phase angle beta is 45 degrees, which gives us this. And when I calculate this out, the value of X2 and thus XB comes out to be a negative 20. Because this reactance is negative, we know it's a capacitor. Therefore, we use this formula to calculate the capacitance in picofarads. C1 is equal to a negative 1 times 10 to the 12th divided by 2 times pi times the frequency in hertz times that capacitive reactance XB. And as before, our operating frequency is 50 megahertz, and we just calculated XB to be a negative 20, which gives us this. This calculates out to a capacitance value for C1 of 159.15 picofarads. And this is exactly what we got with the Smith chart. Now we can move on to the next and final component of our T configuration impedance matching network. And now we have the equation for X3. X3 is equal to the square root of the quantity R1 times R2 minus R2 times the cosine of beta, all divided by the sine of the phase angle beta. And we know that R1 is equal to 10, R2 is equal to 20, the phase angle beta is equal to 45 degrees. And putting these values into our equation for X3, we get this, which gives us the unexpected value of X3 of 0. But this is a series combination of XC and the load's series reactance. To disentangle these, to arrive at a value for XC, we simply subtract the series reactance of our load from X3. And we know that the load's series reactance, XL, is equal to a negative 15, and X3 is equal to 0. So XC is equal to 0 minus a negative 15, which gives us that XC is equal to a positive 15. Notice that the reactance is positive, which means that this is an inductor. And we find the value of this inductor in nanohenries with this formula. L2 is equal to 1 times 10 to the 9th times the inductive reactance XC divided by 2 times pi times the frequency in hertz. And we know that XC is a positive 15, and we know the operating frequency is 50 megahertz. Putting these values into the equation, we get this. And with a bit of calculation, this yields a value for L2 of 47.746 nanohenries. Now, when we use the Smith chart, we arrived at the same value. What this tells me is that I chose a phase value to use here that is the same as the one implied by our path around the Smith chart. Now, I'm going to move on to the final check. I'm going to calculate the input and output impedances of this matching network. The overall circuit looks like this from an impedance perspective. I will calculate the input impedance first. This assumes that the output is terminated with the load impedance. So, it looks like this. Now, I will work through this together with you one piece at a time. You will find the complete equation for the input impedance in the downloadable Go Along with the Video formula sheet. You'll find the link to this sheet in the description. The first thing I see is that the load impedance is in series with the reactance of the output inductor L2. I'm going to call this series combination ZOE. So, ZOE is equal to our load impedance plus JXC. And with our load impedance equaling 20 minus J15 and XC equal to a positive 15, this gives us that ZOE is equal to 20 minus J15 plus J15. So ZOE is equal to 20 plus J0. Now, as we look at the resulting schematic, we can see that this ZOE is in parallel with the capacitive reactance of C1. I will call the impedance of this parallel combination Zm. So Zm is equal to ZOE times JXB divided by ZOE plus JXB, and with ZOE equal to 20 plus J0, and XB equal to a negative 20. Filling in these values, we get this. And using OCTAVE to do the complex math, I get that Zm is equal to 10 minus J10. Now, we're almost there. Lastly, we can see that Zm is in series with the inductive reactance of L1, and that this is the input impedance. So the input impedance is equal to Zm plus Jxa. And with Zm equal to 10 minus J10 and Xa equal to a plus 30, we get that our input impedance is equal to 10 minus J10 plus J times a positive 30, which gives us an input impedance of 10 plus J20. This is the complex conjugate of the source impedance of 10 minus J20. So far, we're on the right track. Woohoo! Next, I will calculate the output impedance. Well, now we're going to calculate the output impedance. Now, when calculating the output impedance, the input must be terminated with the source impedance. And so our circuit looks like this. Like with the input impedance, I will take this one step at a time. The complete formula for the output impedance is in the downloadable Go Along with the Video formula sheet. You will find the link to this in the description. So what's the first thing that we see? I see that the source impedance is in series with the inductive reactance of L1, which is Xa. I'm going to call this ZIE. So we have that ZIE is equal to the source impedance plus Jxa. And with the source impedance equal to 10 minus J20 and Xa equal to a positive 30, we have that ZIE is equal to 10 minus J20 plus a J30, which gives us that ZIE is equal to 10 plus J10. Looking at the resulting schematic, we can see that this impedance is in parallel with the reactance of C1, which is XB. We will call this Zn, and this means that Zn is equal to ZIE times JXB divided by the quantity ZIE plus JXB. And we know that ZIE is equal to 10 plus J10, and XB is equal to a negative 20. Putting these values into our equation, we get this. Using OCTAVE to do the complex math, we find that Zn is equal to 20 plus J0. Well, kind of a surprising result, isn't it? And now, finally, we get to see that this impedance is in series with the reactance of L2, which is Xc, and that this is the output impedance. This means that our output impedance is equal to Zn plus Jxc, with Zn equal to 20 plus J0 and Xc is equal to 15. We get that our output impedance is equal to 20 plus J0 plus a J15, so the output impedance comes out to be 20 plus J15. This is the complex conjugate of the load impedance of 20 minus J15. Exactly, perfectly, Right on. Well, as you have seen here, the process of designing a T-configuration impedance matching network using the equations, well, it's a bit more labor intensive than doing it with the Smith chart. But if you mastered this way and the Smith chart version, then you now have two ways to design a T-configuration impedance matching network. If you found this video helpful, please click on the like and subscribe to the channel. Thank you so much for watching. Until next time, Toodle-Oots.